Hi, everybody. I'm Francesc Campoy Flores, and today we're going to be talking about all the ships in the world and Go. So I'm not a dev for cloud. I'm a dev for Go, a programming language that you might have heard about. I was here last year, and this year there's a lot of Dart people. There's also another Google language, is Go. If you're interested, talk to me. And I'm also a cloud lover. And actually today I'm going to be talking about this project that we prepared for Google I/O last year, and how we created this project from scratch and everything that we learned by doing it. So what have we done? We've done this big mess. So what is this? This actually, right now, you can see here 70,000 ships moving around the world. And that's around 400 million points on a map. That's cool, but how do we get there? So it's simple. We have ships, and then we have the cloud, and then we have a map, and that's it. So that's easy. Now, we're just missing the middle step, the cloud, the magic part of it, and that's why this talk is going to be about. So the first part in my slide before, it's this AIS ship tracking. What's that exactly? Most of the ships in the world have this AIS system. You can think about it as a GPS system, except that it's way older and archaic. Actually, ships very often, what they do is they write their ID, and they send their position all around the world. So sometimes they just write the wrong number, and you see ships flying all around the world and things like that. So it's not a very good source of data. And it has also a problem. It's line of sight, meaning that if you don't see the ship, you cannot get that information. So it's very useful to help ships avoid colliding against each other, but that's pretty much it. But luckily, we have this SpaceQuest system that allows us to, there's actually a group of satellites flying around the world. And the cool thing about flying around the world is that your line of sight, what you can see is way bigger. That means that actually you have these boxes flying around the world and recollecting this data. And SpaceQuest is an agency that provided this data to us. We also had some data from Boston, Massachusetts, so from the lakes. It's a pretty interesting set of data. It's a lot of ships working and going to some place, fixing some cables, coming back. Then we have an antenna in San Francisco, and that's one of my coworkers. And I have another antenna in Sydney. And that's the blue thing, that's a gopher. OK, so the title of the talk is Go See All the Ships in the World. It's actually fake. It's not all the ships in the world, but pretty much. Small ships don't need it, but any fishing ships, and as soon as the ship is big enough, we'll have it. But recreational small ships and private-owned ships normally don't have it. But they can install it, of course. OK, so the problem with this is how much data we have. We have a lot of data here. And the quality of the data, it's pretty bad. And the fact that we have different systems getting all this data, which means that for a single ship, when it sends one position, we may get it more than once. So we have to get all of that into account. The first thing that we have to do is to store all that data. Okay? We have all this data that's coming from different systems, and we have to store it somewhere. We decided to store it in cloud storage, because this allows us to have ACLs, meaning that we can actually say, OK, this provider is able to write into this folder, and don't modify. It cannot modify any files that other people are providing, or it cannot read. So this actually helps us make sure that all the data is sent without being corrupted and kept private if we need it. Now, the problem is that the data we get from the ships looks like this. Awesome, right? So the problem is that then you see, it's like, OK, I'm going to now do a SQL query on this. Good luck. So this data, it's actually, it's called AIS data, there's actually a library, libAIS, that was written by one of the members of the project, Kurt Schwer, and he wrote it in C++. So we had this library in C++, and we wanted to have everything on the cloud. So we're like, oh, yeah, sure, we're going to use everything together, and we're going to put it on App Engine. And then we realized that you cannot run C++ on App Engine. So what did we do? So it's actually pretty simple. What we did, we actually covered on a little bit of a layer of Python, and we ran it on Compute Engine. This allows us to have very easy machines. Like if we need more, we just start a new one. And you can run any language. So we have a mix of Python and C++. C++ because the library was already written there, and Python because Kurt decided that it was the language that he wanted to use. I asked him to do it in Go, but he didn't want to do it. And also because we have the service accounts are very easy to use, meaning that our machines could actually have very easy authentication system to access cloud storage. So getting Compute Engine to read from cloud storage was easy. We could get that data, convert it to something understandable, CSV, and write it back to to cloud storage. Now what we have is all this huge amount of data in CSV. So now we have columns. But having columns now, what could we do with it? We could be able to, we could just put everything into a data file and text file and just go over it and put it into a big SQL relational database. But the problem with that is that it's not really scalable. If we were going to try to get a lot of data all together, all of a sudden, it starts being really complicated, especially if you try to do it in your own computer, as we did at the beginning. It's definitely not a good idea. So how do we extract information out of this huge amount of data? We decided to use BigQuery. Why did we use BigQuery? I don't know how many of you have used BigQuery, but it's actually really impressive. You get to process a huge amount of data really, really fast. And when I say a huge amount of data, is that in this case, for instance, this is actually not the whole data we have. We have more than this right now. But at this point, we had 70 gigabytes of data with 374 million rows. And we execute this thing, which is just an SQL query, pretty much. What we're doing is actually getting, for every single ship, we want to have the average position, latitude and longitude, every single hour. Okay? In addition to this, we actually later we added some filters to say, okay, if the standard deviation of the positions is too high, probably it means that the GPS is faulty. So we're going to just remove this point. Adding that is actually really easy. And why is it really easy? Because you can run this query on all the data we had, 70-something gigabytes, and it takes 5.8 seconds. Only 5.8 seconds. That's pretty amazing. And something that is pretty cool is that you can see it processed only 14 gigabytes. Why is this? It processes only the information that we actually care about, meaning that if there's a column that you are not accessing, you won't pay for the data that you are not accessing. You are just we only count the data that you are actually using. So how do we load? We have all this data in cloud storage and want to load it to BigQuery. How do we do it? So it's actually really easy because they share storage space. I mean that to load something in BigQuery, we just have to tell BigQuery, okay, I want to load this file, and it would just do it really, really fast. And it's just a REST API. So to load this, what we did was we have bucket notifications. Bucket notifications are a feature of cloud storage that allows us to have a notification every time that a bucket, you can think of a bucket like a directory, pretty much, but it's more flexible. Every time that a bucket changes, there's a new file, or a new file changes, or it's deleted, we get a notification. And you can set the notification to any URL. So what we did is, that URL was actually pointing to our App Engine app. And that App Engine app would, every time that it gets that notification of there's a new file, it could send it to BigQuery and ask BigQuery, OK, I want to load this file. Now, what happens if that fails? Because this is the cloud. Everything can fail any time. So something that is really nice of task queues and task queue API is that when something fails, it's retried again automatically. You can define different parameters and say how often do you want to repeat it or the number of times maximum that you want to try it. But by default, what we did was just leaving as it was, meaning that it repeated, I don't remember exactly, but I think it's like every 5 minutes, something like that we had, and forever. Meaning that at some point, I introduced a bug. That happens. And it means that actually our calls were not working. We didn't lose any data. The data was still there. What's in the task queue waiting for us to process it correctly. OK. Now we have all this data, and we want to be able to serve it. We want to be able to serve it, and how? We want to be able to serve it fast, of course, and we want to be able to show it everything in the map that it's going to be interactive, meaning that we should be able to let me show you this video. We want to be able to do something like this. I wanted to do a live demo, but the Wi-Fi is not really good, and there's a lot of data, so it can be a little bit difficult. But you can see here, we're seeing all these little points. We cannot see it much, but we're seeing all these little points moving around. Every single point is a ship. At the beginning, we don't have a lot of data because we filtered data that is pretty old. But if we go on later on the video, you can start seeing way more data. Something that is interesting is that you see that thing on the right corner, on the right bottom corner. If we move it around, that could actually change the data that you're seeing instantly. You don't have to wait for it to load new data. It just shows directly. And the same thing if you want to zoom into the map and pan around, it would just show it directly. Whoop, sorry. Whoop, sorry. There you go. OK, so everything that we have, all the data that we have, is now on BigQuery. So therefore, it could be really easy to say, OK, we're just going to have our web API. So we're going to, our map API, sorry. And with JavaScript, we're going to go to BigQuery, load the data, and just put it on the map. So that works, but that means that every time that we have a query, we have to load all the data, and that takes around 5 to 10 seconds. And you can imagine if you switch on your map and you click on a different time in the timeline, and you have to wait for 10 seconds to something to appear on the map, people are not going to use that. Definitely not. So what can we do? With this architecture, not much. That's it. Except, well, BigQuery actually has an internal cache. So if you do the same query twice, you will very probably get the cache version. So it'll be way faster. But still, we don't have many options to improve this architecture. Now, we add something in the middle. Does it make it faster? No, it actually makes it slower. But now we can do more stuff. So having now an App Engine app in the middle, this allows us to have, so our web app is going to be served from App Engine. And every time that App Engine has to serve the new page, it will actually go fetch all the data from BigQuery. Again, this means that we're going to take from 5 to 10 seconds, depending on the amount of data. But we can add data store. What can we do with data store? So with data store, what we're doing is we're using, again, task queue. With the task queues, what we're doing is scheduling every period of time. In our case, we were doing it every 10 minutes to check the information that was on BigQuery. Meaning that every 10 minutes, we go to BigQuery, do this huge query, and obtain all the data that we care about, and load everything into data store. Now that means that when we get a new request, the data doesn't come from BigQuery directly. It comes from the data store. That means that it's way faster. But still, it's not super fast, because we have a problem here. We are serving JSON. And we're serving JSON, and we're serving a lot of float 64s in JSON. And that means that we're actually sending numbers that are from 1 to 360, the degrees of latitude and longitude. And we're encoding them up to, I think it's 13 floating numbers. So pretty high precision that we actually need, because we're showing it in the map. And we're encoding that as text. So instead of being 64 bits, it's actually 14 bytes, 1 byte per number that we're writing. So that's pretty awful, especially because it means that we're sending a huge amount of data, but also that we have to encode those numbers into text. And the worst part, then when we get to the browser, we have to decode it. And we have to decode it from text back to numbers. So that means that this encoding decoding is really bad. Therefore, what we do, we just send binaries. So now we're going to send just binary code. We're just going to send float 64s in binary format. That means that our App Engine app, it will get the data from data store, which is in normal, like in text. Well, not in text, but like the standard data that you could imagine. So if it's string, it's a string. If it's a float 64, it's a float 64. We'll encode all of that into binary, and we'll send it to directly to Chrome, well, to the browser. Now, the browser is able to interpret all that data directly using typed arrays. So JavaScript has typed arrays, and that allows you to say, from this part of memory to this part of memory, all of those are just float 64s. And I want an array of float 64s of that size. And it doesn't have to decode it or encode it, just interprets that as float 64s. But that means that we're encoding from our format in the data store to the binary format that we're sending to Chrome. This is still not optimal. So we add memcache. Now, with memcache, what we're doing is, once we're done encoding our page of data to binary code, we're going to store it into memcache, and then we're going to send it. Why are we doing this? Because now, the next time that we get a query, we're just going to get a blob of data, a blob of binary data from memcache, and just send it back. So now what we have is really, really fast. This a little bit an idea so you can actually see this exponentially faster. So this is actually a big, big difference in time. So we use Go on App Engine, not only just because I'm a gopher, so my favorite language is, of course, Go, but because we needed to have an App Engine app that is very, very performant. And Go is the fastest, it has the fastest instance startup time, because it's just a binary. There's no JVM, there's no interpreter to start, just like a binary that starts executing. So it's actually n times faster than other environments as Python or Java. It's compatible with machine code, meaning that it can be faster. It's not always faster than Java, but it's definitely faster than Python. And it uses less CPU and less memory. So therefore, it's actually cheaper. Running your App Engine app on Go is actually cheaper than Python or Java. And finally, it has concurrency. And why is concurrency so important? Concurrency is very important in this case because we're running everything on the cloud. And when you're running on the cloud, you're doing two things. One, waiting for stuff to happen. So very often, you're going to send a query, wait for the reply. Being able to do that in a concurrent way, just saying, I'm just blocking there, I don't have any callbacks, just like, I just wait for that. That simplifies your code a lot. And being able to use concurrency, it will make all of that run at the same time. So if you want to send 100 queries at the same time, let's say that you want to load 100 pages of data at the same time. Instead of loading one after the other, meaning that if it takes 1 second per page, you could take something like 100 seconds. With a very small amount of lines of code, something around 6, 7 lines of code, actually you can change that to use Go routines and channels and do it all at the same time. Meaning that it will take something around 1 second. Actually, not 1 second, of course, because you actually have to do all the stuff. And it could be slightly faster, slightly slower than 1 second, but way faster than you could be doing it sequentially. I want to show a little bit of Go code. How many of you have ever written any Go code? Wow, 3, 4, awesome. This is a Java conference, so I was not expecting something better than this, so that's okay. So, 1 second. So let's see this piece of code. We have 2 things. On the top, we're creating a memcache item with some value and some key and some expiration. And then we're setting into memcache. So pretty simple, just setting a key with a value into memcache. And that returns an error. That error could be nil or not. If the error is not nil, it means that something bad happened. If something bad happens, we just log it. So we say memcache failed and the reason. Okay, pretty simple. Now, what happens if we want to add some timeout? Meaning that if this takes more than X milliseconds, I just want to bail. I don't want to wait for it. Well, we can actually add these things. So let's see what we're doing. We're creating a new channel of errors. So a channel of errors is just like a type pipe that it's the way Go routines, or threads, if you can think about it as threads, communicate between each other. So we create this channel of errors, and now we're going to do the memcache set in a different Go routine, meaning that it's actually executed in the background. And when it finishes, it sends the error of the memcache set into the channel. Then the other Go routine, the main Go routine, doesn't wait for that part to finish. It goes directly into the error equals something. So what we're doing there is actually reading from that channel. Now that means that to finish that operation, we have to wait for the other Go routine to write. So we're actually doing exactly the same thing as before. Okay? We're just doing it more complicated, but we're waiting for the memcache to finish. But now we can add very easily a select statement. And a select statement is something like a switch, but it allows you to do things on different channels at the same time. Now what we're saying is, if we can read something from the error channel, that means that the memcache finished. And that's an error. If the error is not nil, that means that something bad happened, and we're going to log it. But the second case is, if 1 second passes, then we can do something else. And if 1 second passes, we just say, OK, the memcache timed out. So this is actually something that we've used to read from data store and memcache at the same time, and just get the fastest thing, which normally it's, of course, memcache. We also use the same mechanisms to read and write concurrently into data store. So this is the final architecture. We're going to go through it little by little. So at the beginning, we have all those ships sending data either through antennas, some institutions that are helping us, or Space Quest with those boxes flying around. That data, it gets to cloud storage using Cloud Data Logger, which is pretty much just something that uploads that data into data store. That creates a bucket notification because it says something new happened. There's a new file. That's added into the task queue through task queue API. And then Compute Engine will know that there's something to process. It will get that file, transform it from weird language that they use to CSV, sorry. And they will save that into the cloud storage again. Saving into cloud storage will generate a new packet notification that will go again to App Engine app, and then App Engine will know that that's a CSV file, therefore it has to be loaded into cloud storage, into BigQuery. So that's the loading all data and processing it. Then we have an App Engine app that it's actually reading from BigQuery every 10 minutes, 5-10 minutes, and getting that huge amount of data, saving it into the data store, and every time that gets a new query, saving the result of encoding that into binary into memcache. And finally, serving it to Chrome. Now, we have now a huge amount of data. What can we do with it? So, Brendan Kenny is the developer advocate that was working for in this project on the Maps part. And he used Google Maps API, WebGL, and the canvas layer especially. He gave a very interesting talk in Google I/O that you can find pretty easily by looking something like displaying all the ships in the world. And the first thing that we did was displaying this. So these just all the latest positions of all the ships in the world. This is something around I forgot the number now, but I think it was 75,000 ships. So we have now 70,000 ships all around the world. That's pretty useful data. It allows you to see what's more busy, what's not more busy, but that's it. It's not really, really interesting. We could show more data, because actually what we're sending is not only the position. What we're sending is, we're sending the current position, so latitude, longitude. We're sending also the speed, the bearing, so if it's going north, south, east, or west. We're also sending an MMSI, which is the ID of the ship. We show also all the data we don't care about, but we also send all the data as the speed over the water, the speed over the sea, no, over the ground, meaning that you can actually find out the conditions of the sea by the data that we're getting from the ships. And this actually, we're showing all the ships by speed, and all the little positions all the little dots that are being displayed on the map, they're being computed by the, not the CPU, but the GPU, sorry. So it's being computed by GPU. That means that while we're displaying all of that with the GPU, the CPU is not doing much. So what we're doing with the CPU is computing this histogram. The histogram is actually showing us the amount of the percentage of ships that are traveling at some speed. So we can see that most of the ships in the world travel something around 12 knots. That is actually not that fast. And we cannot see it here, but it could be actually higher than the whole map. That's all the ships that are not moving. The ships that are not moving, there's a lot of ships that don't move. One kind of ships that don't move are lighthouses. There's also all the oil platforms, and there's also a lot of ships that are actually not moving. So something interesting is that if we display this area, you have a lot of different ships all around, so you can see pretty much all of them going pretty fast. We have a big area of the ocean. But if it goes center, so this is the Gulf of Mexico. And in the Gulf of Mexico, you can actually see the color. Some of the dots are very light blue. These ships that are very light blue are actually showing us, there's two things. One is oil platforms. They're in the middle, and they're, of course, not moving, so they're actually white. But also all the ships that are servicing these platforms. And they actually travel pretty slow. And then there's a huge amount of ships. They're just enjoying the sun, so they're not going really fast. That's why this Gulf of Mexico, you can see a lot of touristic ships all around the coast. And that's why you can see on the histogram, you can see that there's a lot of ships that go 12 knots. That's the normal speed. But also, a lot of them are actually going 5 knots, so like the ships are very slow. Then we can do also, we can color by position, and by, this is the latest position, not the past, but latest position, and color by orientation. This allows us to see interesting patterns. Like for instance, we have in Spain right here, you can see that red are all the ships going north, and light blue are all the ships going south. And this actually allows us to see that even for someone that doesn't know much about ships, like me, we can already understand that there's some rules there. You cannot go with a ship and just decide whatever you want to do. There's actually some channels that you have to follow. Then once you're in the Mediterranean, you can do pretty much whatever you want. And then also you can see this, the region of Indonesia, and from India to Indonesia, you can see pretty much the same thing from east to west. So ships going east normally goes on the southern part, and then the ships going west go on the northern part. So all of this information and more, you can find it on the Google Maps, so the Maps API, so especially the Canvas layer, the Canvas layer, which is how we made this work, and Maps API. Also, there was a different project that was added on top of this, which was we added the protected areas. So you can imagine that once you have all this information, finding out different patterns of ships is actually pretty simple. So one of the things that we were able to discover were ships that were fishing. So you can find that pretty easily because if we see the map here, there you go. You can see up north, north of Sweden, you can see these ships that go north and go all around and go back. Those ships are actually fishing. And with the Maps engine, Maps engine, you can actually show data stored somewhere else into the map directly. One of the things that we displayed was the protected zones, so zones where you cannot fish. And you just do the intersection, and you can find all the ships that are fishing in protected areas. Surprisingly enough, most of the ships could actually disappear when they're getting into protected areas because they can actually turn off the GPS if they want to. So of course we didn't find any, but also something that we discovered too on the lake zone, so right here. We were able to discover some ships that were broken, and we could actually be, we're not doing it now, but it could be pretty simple to create a system where we can find out that a ship is broken and notify people around so they can go help even before the ship knows it's broken, or even the ship let us know. We can actually see the ship is just going with the water. The speed that it has is exactly the speed of the water, so there's something wrong with that. Then all the information about cloud, you can find it on Google Developers, the page. And finding all the information for Google Cloud, for Go, you can find it on golang.org, or I will be later on at the booth. So I'd like to thank you, and I'd like to, if you have any question, there's a mic right there. Thank you.